Hello, and welcome. If you're watching this video, you missed day 1 of week 3 of our computer science principles class. And this is a brief recap of what you missed. So here we go. We started with a quick warm-up. Then we talked about octal and hexadecimal number bases. We didn't quite get to cover overflow and underflow errors, so we will look at those next class. And then I gave you some time to practice. Your objectives for today are that you can freely convert among binary, decimal, and octal. And if I gave you a different kind of base, I wouldn't expect you to naturally be able to get to it right away, but you should be able to figure out how to get to it eventually. And this is something we're going to achieve throughout the class, is seeing the value in these other number bases, and that'll come from seeing them in action when we talk about topics where they're useful. So that'll come in the future, not quite today, but we will get there. Our warm-up for today was to think about this question right here, pick a shape out of square, triangle, circle, and write it down, and then do the same thing 4 more times, so you get a total of 5 shapes. The idea is, how many different ways is there to do that? Well, if you think back to our previous assignment from a little while ago, last week, if you had a choice of 3 shapes, one way to think about this would be to say, all right, well, if I choose one of those shapes, right, circle, square, triangle, and then I was to choose again, I'd have 3 options on top of these 3 initial ones, once again for circle, square, and triangle. And I could keep doing this. I'd have 3 options again for each one. So really what you're going to have to do is multiply 3 for the number of options for the first task, times 3 for the number of options for the second, times 3 for the number of options for the third, and so on and so forth. So you would need to do 3 to the 5th to get the correct answer here. The reason we did this is we wanted to refer back to the previous time where we talked about this, and some people were getting this confused, and they were saying it was 5 to the 3rd. That is incorrect. You need to stop and think about what you're actually doing when you're multiplying these numbers. It's the number of possibilities in each spot, not the number of shapes. So really important that we get that right. Okay, so that's that. Let's keep going. Our next topic here, or next order of business, is to talk about other popular bases outside of decimal, which we're used to, and base 2, which we talked about. One possible base that you might be interested in would be octal. Octal uses regular numbers, or the symbols we're used to, from 1 to 7, and also, some of you said 8. If you said 8, that is incorrect. Just like the base 10 number system does not have a single digit for 10, we have to use 2. Similarly, a base 8 number system would not have a single digit to represent 8. You would need to use 2 digits. But you do need a 0. Remember, any number system without a 0 does not work. You must have 0 to keep track of place values. Alright, so we have our 8 symbols here. Let's think about how we can put them to use. So if we were to convert 24 base 10 into base 8, how would we do that? Well, one simple way to think about it is in base 8, what you would have is you would have place values that are powers of 8. So the first place value would be how many 1s you have. The second place value would be how many 8s. The second or third place value would be 8 squared, right? This is really 8 to the 0. This is 8 to the 1. So we can keep doing this indefinitely. So let's think about how we can convert 24. Well, let's see. What power of 8 fits into 24 nicely? Well, an easy thing to think about would be how many 8s fit into 24, right? 64s do not fit, so we don't need any of these. So we need some of these. And if you think about it for a second, 3 times 8 is 24. So there's actually 3 8s that fit in here and 0 1s. So this was fairly trivial because 24 is actually divisible by 8, so it's a little easier. But what happens if we have a trickier number? Well, in a second, we're going to take a look at a systematic way to do this, conversion type stuff, using binaries in an intermediate step. And let's see how that works. All right. So the next number system we'll consider is hexadecimal. Hexadecimal is base 16. In hexadecimal, the trickiest part is that there's a single digit that we need to have to represent the number 10. In our system that we're used to, 10 is two digits. It's a 1 and a 0 placed together, and we know that it means 10 because the second place value always represents the number of tens. Well, in this particular case, if we were to write 1, 0, it would really mean 16. So we want to be careful. In order to represent 10, we need a single digit. We're going to use the letter A to represent 10. Then 11 is B, 12 is C, and so on and so forth. F is 15, the highest number you can represent with a single digit. All right, so let's try a similar feat. What is 24 in base 16? Well, we just tried base 8. Let's try base 16. To do base 16, we need to keep in mind that once again, we're going to have various place values that are powers of 16. So we're going to have a 16 to the 0, or our ones place. We're going to have 16 to the 1, and then 16 to the 2, and so on and so forth. Hopefully we don't need those for 24. So how many 16s fit into 24? I hope you guys all agree that at least one will. So if we take away 16 from 24, what do we have left over? Well, we have 8 left over, right? That means we have 1 16 and 8 ones, or 18 base 16. Oftentimes when you write numbers in different bases, you will use a little subscript to tell the person reading what base you're using. This is base 16. All right, there you go. 18 is the correct answer. So now the question is, these are really tricky to kind of calculate by hand. Is there an easier method? And there is. Why are we talking about these? They play nicely with binary. How do they do that? Well, there's an easy way to convert from binary to octal and from binary to hexadecimal and also backwards. And the reason for that is, some of you may have realized, 8 is a power of 2, and so is 16. And since they're powers of the base of the system we're going to be converting to and from, there's a nifty little trick that you can use in terms of how you convert. So let's think of a number. We're going to look at 01011 in binary, which I hope you all agree is 11 in decimal. And we're going to figure out what it is in octal. You could do it manually just by doing some math, right? So if we start at 8 and then count up to 11, I hope you agree that we'll need 3 more numbers. So we need 1 8 and 3 1s. So that all checks out. But how would we do this in an easier fashion? Well, what you can do is you can take these numbers, the binary digits, and you can regroup them into groups of 3, always grouping from the right. So break up the numbers into groups of 3, starting from the right. So we have 1, 1, 0, reading from right to left here. This would be one little triplet. And the next little triplet, we don't have enough numbers here, but remember you can add as many leading zeros as you like to a number and it does not change its meaning. So we would have 1, 0, 0. All right, so if I break these up into these two groups, some of you may have noticed that in fact, these correspond to the digits of our answer. They're just smushed together. So 1, 1, 0 is the same thing as add 1 to 2 or 3, which is over here. And this is, of course, 1. This works for any size number, not just 2-digit, not just 1-digit, but as many digits as you want. Why does this work? Well, think about it for a second. In binary, this is the ones place, 2s, 4s. The next place would be the 8s. And just like an octal system, if I was to use these to their maximum capacity, the highest I could count to would be 7. So indeed, these actually, in an interesting way, represent place values in the octal system if you break them up into little triplets like this. These are powers of 8, and it would continue to be true no matter how many of these you introduced. So that is how you do the octal conversion. Here are some problems you can take a look at and practice. I will not belabor you with doing those here. If you have questions or want me to go through them, please send me an email. Alright, so how does hexadecimal figure into all of this? Well, it's very, very similar, but we have to think about what 16, uh, or how 16 works in binary. Before with octal, we needed groups of 3. If we're dealing with 16, some of you may have realized we need groups of 4. Why do we need groups of 4? Well, we have the 1s, the 2s, the 4s, the 8s. The next place would be the 16ths. And if we were to turn all of these into 1s, I hope you agree, that would represent 15, which is, of course, the largest number you can get in a single digit in base 16. Alright, so let's try it. We have this binary number. If you use your flippy-do, you can convert it into decimal. It's 155. And we're going to make the case that it's going to be 9b in base 16. Let's justify that. Break the numbers into groups, starting from the right. Always go from the right. So we're going to have 1, 1, 0, 1, 1, 0, 0, 1, like so. And then we need to convert them into hexadecimal digits. Now this is the trickiest bit that trips up the most people. Do not accidentally write 11 here, even though that is what this means. You need to keep in mind that in hexadecimal, 11 is a single digit, so you need to be writing B instead. This, of course, over here is just 9. 8 plus 1 is 9. So altogether, I hope you all agree that this all turns out to be 9b. To go backwards, you would simply do the reverse. You would take your digits of hexadecimal and split them up, and then write 4 binary numbers to represent each one. Now the tricky bit comes when people forget to include leading zeros. So I'll show you one example going in hexadecimal, going backwards, going from hexadecimal to binary. So let's try it. If we take a hexadecimal number, let's say A5, that's a hexadecimal number, right? Base 16, we're going to convert that into base 2. How do we do it? Well, what you want to do is you want to break apart your digits. So, not quite what I wanted. A5 is what I wanted. So let's go ahead and go for it. So 5, how do we represent that in binary? Well, we're going to need a 1, no 2s, a 4, and then here's where mistakes most often happen. We need to make sure we use 4 digits. So we need to add leading zeros until we have 4. So you need to write the 0, otherwise this will not work. And then A represents 10. So how do we represent 10 in binary? It is 0, 1, 0, 1. Ta-da! This is 10, this is 5, and if you were to actually look at this number and convert it into decimal, and then convert this into decimal, you would see that they match up. I'm not going to do that. I will leave that to you to do if you would like. Okay, so what are we doing with all of these? If you look on my CPS, there are 2 assignments for you to do. One is titled 010401 binary practice. It is due by Tuesday at midnight. It is worth 20 points. Please don't forget to do that. That was assigned last week, so you should have had a little bit of time to get started on that. And then the second assignment here is posted under week 3. It is titled 010402 conversions, and this has a number of different kinds of conversions in it. I always recommend you use binary as an intermediate step, even if the conversion does not ask for binary. Like if you go from octal to hexadecimal, use binary as an intermediate step to get from one to the other. And this is going to be due September 18th and is worth 20 points. That is everything we wanted to cover today. Please let me know if you have any questions, and I hope you guys have a fantastic rest of your day.